In this video, we're going to take a look at the details of how Niels Bohr came up with his model of the atom. Because he's looking at differences in the amount of energy that an electron has between the two orbits, he needs to be able to find that difference, to find out how much energy an electron has when it is in an orbit. The total amount of energy that it has in an orbit would be equal to its positional energy, the energy of where it is, its position, and its kinetic energy, because these particles are moving as well. So he sets out to figure this out. Positional energy is equal to the work that it takes to get a particle into its position. This is a physics thing that every physicist knew. It applies to large objects and small objects, and so he assumed that he could use that with particles like electrons and protons as well. And the work that it takes to move an object into a position is equal to the force that you have to apply to move it times delta x, which is the distance that it moves. Now for an electron, if you imagine that being moved out to its radius, the distance that it gets moved is the radius. And so he needed to know what was the force that had to be overcome to move it out there. Well, these are charged particles, and they obey Coulomb's law. This turns out to be a very important law in chemistry. You're going to see this more than one time again in this class. But the electrostatic force is equal to a constant number times the charge on the first object, that's Q1, times the charge on the second object, that's Q2, divided by the square of the distance between the two objects. That's Coulomb's law. And that's the force that attracts charged particles to each other. So in this situation, the electrostatic force that's holding them together, that would have to be overcome to get that electron in its position, would be equal to that constant number times the charge on the nucleus. Well, the charge on the nucleus, we're going to call that Z. Now for hydrogen, Z is just 1. It's just one electron charge, because the electron and proton have the same charge. Times the charge on the second, which is the electron, so that's just E, divided by the square of the distance between them. But what's the distance between them? It's the radius, so radius squared. So with E being the charge on the nucleus and negative E being the charge on the electron, then the electrostatic force comes down to negative ke squared over r squared. But remember, the positional energy is equal to the force times the displacement, and the force is equal to negative ke squared over r squared, as we just saw, and the displacement is radius, as we saw earlier. So when you put that together, multiplying r by this number, this ratio, one of the r's cancels, so that tells you that the positional energy is equal to negative ke squared over r. So put a pin in that. We're going to come back to it later. Now it's time to work on the kinetic energy. For a single point mass orbiting in a circle, the kinetic energy is given by this equation here, 1/2 of a number called I times omega squared. And omega is the angular velocity. In other words, like how many revolutions per second or something like that. So a measure of how fast it's going around, spinning around in a circle. I is a characteristic of the spinning object, which for a point mass is the mass of the object times the radius of the circle squared. That's I. Omega, the angular velocity, turns out to be, if you're measuring it in radians, the ratio of the linear speed of the object divided by the radius of the circle. So if you put that together, remember I is mr squared, and remember omega is the ratio of v over r, so that's squared. So you put this all together, and you're going to get that the kinetic energy is 1/2 m r squared times v squared over r squared. And the r squareds cancel, and so the kinetic energy of this particle is mv squared over 2. So then if you add the positional energy and the kinetic energy together, you get minus ke squared over r plus mv squared over 2. But there's a problem, and that problem is that Bohr doesn't know two of the things in this equation. He doesn't know the radius of these orbits, and he also doesn't know the velocity that they're going to be traveling with. So there's a little bit more thinking to do. Another thing that they knew about objects that were spinning around in a circle, in a circular orbit, was that the centripetal force on any of those objects was going to be equal to the mass of the object times the velocity of the object, the linear speed of the object squared, divided by the radius of the circle it was spinning in. And this is negative for reasons of definition. Negative would be towards the center of the circle in these centripetal forces. But what is the centripetal force that's holding this together? It's the electrostatic force. And remember, the electrostatic force, well, that was K, negative K, times E squared divided by R squared. That's just Coulomb's law applied to a single electron with a proton that is the nucleus. So that is equal to negative mv squared over r. So this becomes mv squared is just equal to ke squared over r. So going back to our original energy equation, energy is positional energy plus kinetic energy. The positional energy, remember, was minus ke squared over r. The kinetic energy was mv squared over r, but now we have seen that mv squared is ke squared over r. So this equation becomes the total energy is equal to negative ke squared over r plus ke squared over r over 2. So ke squared over 2r. If you add this together, you get negative ke squared over 2r. That's the total amount of energy that an electron has in its orbit. So what don't we know? We do know K. That's a universal constant that everybody knew. We know the charge on an electron. Millikan figured that out. We don't know the radius. So we have to do still some work. Bohr's real insight that helped him develop this model was recognizing that those line spectra meant that the energies of the electrons in the orbits had to be quantized. And he's already looked at how to, kind of evaluate how much energy is in these little rotating particles. But the part that's new, the part that he had to just sort of insert here, was the quantization part. So basically, Bohr just makes this up. He says that the kinetic energy that the particle is going to have is going to be equal to a number, n, that he's, it's a quantum number, 1, 2, 3, 4, 5, 6, 7, 8, up to infinity, but whole numbers only, times Planck's constant times frequency divided by 2. It's not completely true that he just made this up. He had good reasons for this to be a guess, but it was kind of arbitrary. Kinetic energy is 1/2 mass times velocity of the particle squared. So that means those two could be set equal to each other. And velocity is distance divided by time, and frequency is 1 over time. It's just the reciprocal of time. So if you put this together, you can start to make some headway here. So first of all, what's the distance that's being traveled in an orbit? Well, it's 2 times pi times the radius of the orbit, because it's a circumference. And if frequency is 1 over time, then that means time is going to be 1 over frequency. So to get velocity in other terms now, we could just say that velocity is equal to 2 times pi times r divided by time, but time is 1 over frequency. So that means velocity is 2 times pi times r times frequency. Now let's solve this for frequency. So frequency is going to be equal to velocity divided by 2 times pi times r. So now let's set the two kinetic energy equations equal to each other. mv squared over 2 is one way of expressing kinetic energy, and that's equal to n times h, Planck's constant, times frequency divided by 2. But we can substitute here because we know what frequency is in terms of velocity. So mv squared over 2 is equal to n times h times velocity over 2 times pi times r divided by 2. And that could be simplified on the right-hand side there to n times h times velocity over 4 times pi times r. And remember, that's equal to mv squared over 2. So we could take a 2 out. We could take a velocity out from both sides by canceling. And then that's going to give us that n times h divided by 2 times pi times r is equal to m times v. So that means that velocity is n times h divided by 2 times pi times m times r. So r is the radius of the orbit, m is the mass of the electron, and h is Planck's constant, and n, remember, is that number that starts at 1 and goes up by whole numbers. Okay, remember this, mv squared was ke squared over r. Now we have a way of eliminating r as an unknown and just sticking to only velocity. Let's do some substituting. So mv squared is m times, we now know that v is equal to n times h over 2 pi m r. And that's all squared. And then that will be equal to ke squared over r. So if we square the stuff that's in the bracket, we get m n squared h squared over 4 pi squared m squared r squared equals ke squared over r. We can cancel an m here. We can cancel one of the r's. And that gives us this equation that n squared h squared over 4 times pi squared times m times r is equal to ke squared. And then we can solve this for r. And what you find out is that r, when you do a little algebra here, is n squared h squared divided by 4 pi squared m ke squared. So then you can substitute that into the overall energy equation and you don't have r anymore. So we can do that here. It's minus ke squared over 2 times r. But we know now that r is n squared h squared over 4 pi squared m ke squared. Let's continue this up at the top. E, we now know then, is negative ke squared over 2 times the reciprocal of this ugly looking fraction, 4 pi squared m ke squared over n squared h squared. 2 is going to cancel. And then we can simplify this a little bit. It's going to be negative k squared times 2 times pi squared times e to the 4th over n squared h squared. So now we have energy in terms of all stuff that we know. We know k, we know 2, we know pi, we know e, we know Planck's constant. The only thing we don't know is n. And we do actually kind of know n because it's whole numbers. It's 1, 2, 3, 4, 5, 6, up to infinity. So what he did was he saw a way to get towards something like Rydberg's equation by just pulling out all the constants and just separating the n squared term by itself. So when you do that, this is what you get. Negative k squared e to the 4th, 2 pi squared m over h squared times 1 over n squared, where n is a number that ranges from 1 to infinity through whole numbers. Here's all the constants. Stick them in there. Do your calculations, and this is what you find out. The energy of an electron in any orbit n is equal to negative 2.18 times 10 to the minus 18th joules times 1 over n squared, where n is that 1, 2, 3, 4, 5 up to infinity. That constant was called the combined constant, or Bohr's constant, it's now called. That's why they used B probably. So negative B times 1 over n squared. That's the energy that an electron is going to have when it's in any orbit. Now back to the model. Remember, when we're losing photons that create the emission spectrum, it's because we're jumping from one orbit down to another orbit. So we want to look at the difference between the energy in two orbits. So in the low orbit, the energy is going to be minus b times 1 over the low n, which could be 1 maybe. And in the high orbit, it's going to be minus b times 1 over n of the high squared, which would be maybe 2. But n high is going to have to be bigger than n low. So what's the difference between those? The delta E, well, that's equal to the high minus the low. So minus B times 1 over n high squared minus B times 1 over n low squared. So delta E is B times 1 over n low squared minus 1 over n high squared. But remember that delta E is h nu, and remember also that nu is C over lambda, so that means that H times C over lambda is equal to B times 1 over n low squared minus 1 over n high squared. And this should start looking a little bit to you like Rydberg's equation at this point. Now let's divide both sides by H times C. So that means 1 over lambda is equal to B over HC times 1 over n low squared minus 1 over n high squared. This is exactly Rydberg's equation under one condition, and that is that B over HC is equal to 109,737 per centimeters.